with that said, hey, and it's my pleasure to introduce Sam for his PhD defense. It's the end of an era. So for those that don't know me, I'm Laurent Bertrand. I'm Sam advisor. We actually joined the University of Vermont essentially together. I think I had a meeting with Sam before I was officially an employee of the university. So it's been an amazing bunch of years. It's been both a learning experience and a challenge in many ways for both of us. And I think a lot of that is because Sam has such a breadth of knowledge. And even now finishing his slides at the 5 minutes before the defense is like Sam fighting his inner instinct to like add like facts and knowledge that he has about the world. I'll just tell one dumb story. I could tell many, but there was one that like I think about almost every day now. So years ago, I was at the College of Medicine getting coffee. And when you get coffee there's dark roast and light roast. And I'm just getting dark roast because I don't know. I thought I liked it better. And Sam tells me, in all the blind tests, people think they prefer dark roast, but they actually prefer light roast. This is like Sam knowing weird facts about the world. And he like says weird facts about the world all the time, but this one I think about every day now. And it's been 4 years, I think, since that moment, and I've been drinking light roast every day since. And it's like this challenge also in the science. Like I think Sam has this incredible wealth of knowledge about the world, and a lot of it is useful, makes our model more detailed, better, and you'll see a lot of that. Sometimes it also overcomplicates things when you don't quite know when you get into a project what's going to be useful and what won't. So I think this like balancing act is something that's amazing about Sam. I hope that you keep that throughout your career. But for today, I think it's an interesting thing for people to look in the models and sort of see how Sam's knowledge of how things work influences science. So the floor is yours.
Thank you, Laurent. Coming to UVM, starting with Laurent was a real privilege. I initially started quite cynical of certain aspects of network science because of my history at the Minority Health Disparities Initiative, where there was a huge disparity between data and of the collectors and then how it was treated later down the pipeline. And my first paper is a response to me being sort of mad about that. And I think Laurent is a really good tempering force to show me the things that are worth being cynical about, and the things that, they're not perfect, but they work and they can save some lives. And that's what we're going to be talking about today, which is pragmatic interventions against epidemics on networks. There we go. Okay, so I'm going to tell you what I mean by this title. It's pretty short, so we can get through it quickly. Because this is a computer science PhD, I'm going to evaluate the expression from the inside out. We were talking about networks, which you can think of as a modeling tool, a paradigm, a formalism, that are used to study systems whose entities are connected through pairwise interactions, like social networks online, where people are connected to other people they know through friendships or following. And we are talking about negative contagion phenomena that spread that people don't like. Traditionally, epidemics just meant a contagious disease, but as you'll see, we can use a lot of the same mathematical formalisms and methods that I've researched with a little bit of fiddling to do a lot of the same things with other stuff, other negative spreading phenomena. And we are talking about interventions against these negative spreading phenomena. We don't just want to study them, we want to stop them. And so these are methods and strategies to prevent, stop, or mitigate these epidemics. And then specifically in this defense, we are going to talk about designing and researching intervention methods which are actually implementable in practice or approaching that. In the face of all the logistics, costs, politics, steps, constraints, and hoops, which kill so many fun mathematical min-max ideas that we make up as academics, pragmatic is the most important word in the title today. It is the part that takes this from a topic that I know a lot about to me being a leading expert in the field on this topic. As you can see, we've narrowed down the type of papers as we've gone along, and there are no papers indexed by Google Scholar of any year that contain all 4 of these words in their title. So this is the part, this is the word that makes this a PhD. So what was I getting into about getting our hands dirty with realism? A wise man once said, idealism detached from action is just a dream, but idealism aligned with pragmatism, with rolling up your sleeves and making the world bend a bit is very exciting, very real, it's very strong. And this wise man was Bonnie of YouTube. And this is a man who knew how to get his hands dirty. Striking a deal with major stakeholders, making your product freely available, engineering a situation where your album is forcibly downloaded onto one of the top operating systems in the world. These are the kinds of things that you have to be if you want to be pragmatic and actually stop a disease in the real world. You have to work with stakeholders of companies that don't have the world's best interest at heart necessarily. You have to make sacrifices and make choices. Now, this didn't get him rich. It made a lot of people mad, but that's certainly one way of getting your album to be one of the most downloaded albums of all time. It was an ambitious goal, if not necessarily a noble one. But today, I'm here to talk to you about what I think is a noble goal, stopping contagion. Lots of scientists from all over academia have this goal for over 100 years. In epidemiology of humans, animals, pathology of plants, studying things like COVID, avian flu, and birch blight, but also with concepts and methods spreading to a diverse range of other disciplines, studying invasive species, misinformation, and hate speech using similar methods. Among these methods that have spread to other disciplines include those studied by the subfield of network science, in which contagion research has found a home. This is a natural home for this field, as networks are effective modeling tools for any system where spread occurs through direct host-to-host transfer through a well-defined pairwise interaction channels. We call the hosts of such contagion nodes, which can be individual entities like animals and plants, but also more abstract things sometimes like online accounts, farms, or cities. We call the pairwise interactions between these nodes edges, which is the channel through which a contagion can spread. For example, forms of contact like social or sexual contact, or of sharing things like needles in humans or flowers in bees. These are a lot of the things I've worked on throughout my PhD. And as you can see, the network is spreading, a disease is spreading. As such, numerous entities, a negative contagion present both existential threats to society as well as costly annoyances to groups of all scales within it. As such, numerous entities, coalitions, and directives within affected groups exist to deal with the boots on the ground practicalities of defending themselves and us from the encroaching spread. Governments often maintain centers and intergovernmental partnerships to control human and animal diseases, as well as plant diseases and invasive species and pests. Companies establish teams to combat misinformation, and nonprofits of all kinds exist to supplement these initiatives. These organizations face many obstacles in the practical implementation of mitigation interventions that are not always addressed by the corresponding academic research. Besides cost limitations and limits to authority, there are serious and pervasive problems with data about the dynamics of the contagion, like epidemiological parameters, data about the structure of the system on which it is spreading, like the contacts or mobility information of the population, or even the basic state of the contagion, as things like PCR testing can be impossible sometimes, costly, or disincentivized. These types of obstacles are often ignored by the corresponding academic research, as the latter can make strategic propositions while selectively ignoring practical constraints. In our first research chapter, we will look at a corner of the literature where this is quite evident. So this is the first paper I published, targeted or immunization strategies in networks with missing data. So let me start what I mean by intervention. So we're talking about is selecting which nodes in a network to immunize in order to minimize the spread of outbreaks. When we say immunize, what we mean is any measure which will effectively sever all ties a node has and prevent them from becoming infected or infecting others. This can be vaccination, or more abstract things like rehab for people who inject drugs, or bans on social media. There's nearly 25 years of research now on this topic, and one consistent theme is that when choosing nodes to immunize, it is useful to select nodes which are central in some way. Now, obviously, to many, it is effective to remove nodes with the most contacts. That's like vaccinating healthcare workers, perhaps, but it can also be quite useful to vaccinate nodes which interact with many groups of contacts who would not otherwise interact or have a pathway to infecting each other. This could be like teachers who teach science only to all the different homerooms from kindergarten to 5th grade. One metric that captures this concept is betweenness centrality. This figure illustrates how these two strategies would immunize two different nodes first, with the middle red node having the most contacts, but with the yellow node serving as the only conduit for spread between the groups. Now, what happens if to your choice, if there was a single unknown node that you were unable to find in your survey? Immediately, this node becomes the best choice for both betweenness centrality and degree. And it doesn't even have to be a very highly connected node for it to completely change the betweenness centrality choice. With the current approach, most targeted immunization research assumes the underlying networks that strategies are being tested on are complete, as in all the data of all the people in the population and all of their contacts was collected. Speaking as someone who was responsible for collecting and collating this data from limited field notes of people who inject drugs, written in Spanish when I was a 19-year-old undergrad living in Nebraska, not Puerto Rico, where it was collected, who hadn't taken a Spanish class in several years, this data is never complete and accurate. There are a number of reasons for this. If we were talking about a large-scale pandemic like COVID, then collecting all the connections between everyone on Earth is impossible for a number of obvious reasons, with resources and privacy being sunk. Even for small populations where targeted immunization could be extremely useful, like in populations of people who inject drugs or sex workers, these have their own reasons why data is scarce and unreliable. In fact, for these reasons, populations like those I mentioned, for example, are called hidden populations, where the illegality or stigma of the activity that defines the population inherently makes even knowing who belongs to it difficult, let alone who all of their contacts are. One way to mitigate the issues facing global centrality score-based immunization strategies is with what we call stochastic or local strategies, which work without complete knowledge of all network connections. There are many of these strategies, and they get as complex and contrived as the global strategies, but the basic principle behind them is randomly sampling pieces of the network and picking locally important nodes. The simplest example of this is to pick random nodes and immunize their neighbors. This is called acquaintance immunization, and it works because of the friendship paradox, which states that on average, your friends have more friends than you do. The friendship paradox occurs because the probability that a node called an acquaintance will be selected as a random neighbor of a random interviewee is proportional to the number of neighbors that the acquaintance has. The more friends you have, the more likely that you get brought up in some conversation somewhere on any given day. In the example in the corner, the node in the center is 8 times more likely to be selected for immunization using this process than any of the other nodes. However, despite needing only to be able to do random network sampling of parts of the network instead of requiring the whole network, this itself is also often a tall order. There are a few reasons for that, ways that can go down. As the steps involved to get this node list and the complete local information require the interventionist to have a list of nodes to sample from, and then also requires that when they go to investigate the local neighborhood of each sampled node, that they are able to accurately gather the names and contact info for all of their friends, as well as sometimes their friends' friends or more. Even for acquaintance immunization, which requires only 1 interview per immunization, in order to literally get a random friend of the interviewed node, you would typically need the full list of their friends, so you can pick randomly. Now, the feasibility of this will differ depending on the situation. So in our methodology, we examine 4 ways of how this might go down. First, it might be easy. You could have a complete node list and complete local information, but still need to use a local strategy for some reason. For example, suppose a school administration has complete student records and can use school cameras to accurately identify all the contacts of a few students, but doesn't have the manpower to do it for all students and all of their connections. We call this version of what could happen, GG variant, because the sampling frame comes from the complete network, which we call G, and the local info also comes from the complete network, G. Another way it could go down is that it could be very hard. You might not have a list of all the people in the population, and you also might have trouble getting information out of people when you go to sample them. For example, you might have a hidden population of sex workers where you don't have a list of all of them or their clients to sample from. And then when you go to interview people, they might have a client count that is high enough that they don't remember all of them or are not able to get all of their names or contact information to you. We call this scenario G prime, where G prime represents the known network that the researchers are able to collect. And it's G prime because both the node sampling frame and the local information comes from that known network. Then you might have an incomplete node list, but be able to get accurate information when you go to sample the network. For example, it is impossible to get a complete list of all websites on the internet because they're changing and hard to grab. But when you're on a website, you can click all of its hyperlinks. We call this G prime G variant because the sampling frame is incomplete, but the local information comes from the complete network. Finally, you might have the same situation that we just described, where you start with an incomplete node, but you're able to get accurate local information when you sample. And if you're also able to immunize as you go, instead of immunizing all at once at the end, then you can add to your sampling frame of nodes as you hear about them from the interviews, which you have to conduct anyway to choose random sampled nodes. Random sampled neighbors. We call this coupling of network discovery with immunization the G bar G variant, where the bar represents an updating sampling frame. In order to examine all four of these situations, we create four different variants of the simplest stochastic strategy acquaintance immunization, where the missing data only affects the G prime or G bar parts, and we pit these against the two most commonly studied global centrality-based strategies. The general idea and walkthrough of our methodology is this. For each strategy, and across different levels of missing data and other parameters, we test how removing the nodes a strategy tells us to when fed the known network, which is the network available to the interventionists, works as an immunization strategy on the true network, which is the network that's actually affected by the outbreaks. When we simulate these outbreaks, we use an SIR model, which stands for susceptible, infected, recovered, and the nodes can be one of these three states. And then there's a fixed rate of transmission from infected nodes to connected susceptible nodes, and those infected nodes have a fixed change into the recovered state again after being infected. I'll focus on the key findings, since with some exceptions, which I will note, they are consistent across a large suite of test networks, though differences in scale change. This allows us to focus on one example figure for the most part, which is good because this figure is a little bit complicated. So specifically, the example that we're going to focus on is the result of our tests immunizing 10% of nodes on networks generated to resemble the Colorado Springs network of people who inject drugs, which I mentioned briefly earlier. With the infectivity rate of our SIR outbreak model at 1/5 the recovery rate, the 0.2 beta, which corresponds to an R0 roughly equivalent to the seasonal flu for this network. The left vertical axis here is the benchmark of effectiveness that we care about, actually. So it's how much better these targeted immunization strategies are than random immunization. So what this left vertical axis shows is the difference there. So it's the outbreak size of random immunization minus the outbreak size of the targeted immunization, such that a 0 would mean that it's absolutely equal to random immunization, and a higher value is better because it means it saved more cases. For clarity, we also provide this right vertical axis, which matches up. And that's just the absolute mean outbreak size. So note that it's reversed such that this base value for random immunization strategy, which is this dotted line here, stays at 0 here and is corresponding to its constant value 12.97 noted there. A strategy scoring a 0 on the right vertical axis, which these three strategies come pretty close to, would mean that those strategies completely stopped the outbreaks. Using the relative efficacy versus random immunization allows us to naturally talk about how these strategies are decreasing in efficacy as we move from left to right on this horizontal axis, which is the percent of nodes missing from the sample. So as we increase our level of missing data or our data gets worse, so do our strategies which rely on it. So the first key finding to note is that acquaintance immunization, these 4 variants, the strategy designed to be usable without complete network data, it does in fact do that. It is quite robust, even as the level of missing data gets quite high, as long as we assume that we have access to locally perfect information. So when this variant of acquaintance immunization, which both has imperfect local information and an imperfect sampling frame, it declines just as fast as the global strategies. An interesting but unexpected addendum to this robustness is that it's true even if you start an immunization campaign with the local incomplete network and add to your list of nodes as you hear about them, and actually it appears to get better as you increase the level of missing data that you started with. And so as we'll see a lot more in depth later, what happens is that the sampling frame becomes biased because of the friendship paradox. And this bias of interviewed nodes also positively biases the immunized nodes. We're going to explore that in a lot more detail. Except, at least it did on the tested networks when they were highly transitive. When they are, we see that this updating sample acquaintance variant is better than regular acquaintance, GG, which has complete information. When the networks that we're testing it on have high transitivity, even across a wide variety of infectivity levels. But when those networks are low transitivity, in our tests, it did not do better than the complete information acquaintance. Now, as it turns out, the mechanism behind this is not exactly transitivity. This is just what we observed when we ran a battery of tests at the time of publication of the first paper, without understanding fully why. In fact, what we've learned later is that it's because of assortativity, which is implied by transitivity. Assortativity, which means that high degree nodes are connected to high degree nodes and low degree nodes are connected to low degree nodes, makes it so that the positive degree bias of the sampling frame positively influences the neighbors selected from the interviewed nodes, which are the immunized nodes. We explore this principle in much greater depth in the next chapter. The next finding is a bit obvious maybe, but confirms the hypothesis which began the research. While the global strategies are extremely effective when they have complete data, they are not so robust to missing data and decline quite a bit when you get to having a lot of missing data. And this eventually results in a regime shift that's going to happen in different places for various different parameter combinations, but it always happens where eventually the strategies which start not as good but are more robust to missing data surpass the strategies which start better but are less robust. And that's pragmatism in action. Finally, and perhaps even more obvious to many of you, but the most important for the message of this defense, the strongest and most consistent result throughout all networks, all infectivities, all immunization coverages, everything is that target immunization works. Every strategy, even the simplest ones, even at high levels of missing data, are a whole heck of a lot better than random immunization. In this example, the global strategies effectively stop all outbreaks when they have full data, and even when the data is pretty low, the robust strategies reduce it by more than half. In the United States, that would be almost 25 million cases avoided. So what are the practical implications of this? Well, what that means is that despite ignoring a fundamental constraint of the system that they're studying, target immunization researchers have recommended strategies that get a lot done if you were to implement them today. They aren't terrible. Well, they ignored the constraint and still did pretty well. What happens if we don't? What happens if we acknowledge it and build a strategy from there? So let's do that. Instead of taking methods which ignore these inevitable issues, let's build one that leans into it. About that, how are we going to design this strategy? Hey, didn't we say something about a strategy that got better the less data you started with, and we stumbled upon it accidentally? What would happen if we discovered and isolated the mechanism behind it and ramped it up to 11? Let's do it. And we called it S4, which stands for Strategic Synchronous Snowball Sampling Immunization. It is a strategy which synergizes immunization with the sampling that would be required to do that immunization anyway, to quickly find and immunize the highest degree nodes with the fewest number of interviews. S4 begins like any method of network sampling would begin. You start with the nodes you know, and you add to the network by adding their friends, and then their friends' friends, and then their friends' friends' friends, and so on in a snowball. It's been known since the 70s that this leads to a sample bias to be high degree because each step invokes the friendship paradox. But research on this bias is mostly geared toward combating it or understanding it well enough to draw conclusions about the network despite it. But we say, screw that, give us all of the bias. Specifically, how this is going to work is, we start with a small subset of seed nodes as our initial sample, and that's going to be these three green nodes on the step 0. So in the example for people who inject drugs, this might be people that you gain the trust of because you were volunteering at a harm reduction center. And then for each step, you're going to select a random node from your node list to interview. And in this case, that's going to be this one, which is this rightmost node from the seeds. And then we're going to ask them about all of their neighbors, add all of those neighbors to the sample, and then immunize one of them, so note that we've added several nodes to the sample in step 1, and we've immunized this one right here. And also note that one addition that we make to ramp it up to 11 is that even if those nodes are already in the sample, we're going to add them again. This overrepresentation increases the degree bias of that sample, which is going to be beneficial to us. Then, just like acquaintance, you're going to immunize one of those nodes, and you keep doing this as many times as you want. Even as quickly as step 4, we can see that most of the high degree nodes in this network have been found in the sample, and several of them have been immunized. Well, that seems easy enough. So this should be a matter of just simulating it and comparing it to a couple other immunization strategies, like most of the other 1,000 target immunization papers, right? No. So it turns out this simple little procedure is more complicated and more interesting in a way that took me 3 years to fully work through. First of all, that little sequence of steps that I walked through, did anyone notice something that could go wrong with it? No? You sure? Okay, good, because I didn't for a year and I would have been sad. Okay. So it turns out that a complication arises when you try to immunize a node that has already been immunized. You have to make a choice what you do in this procedure in that case. And this wouldn't happen with a large enough network that has a few enough number of immunization units. But if you're working with a small network or you're immunizing a sizable fraction of the network, it does happen fairly frequently. So in that case, we're just going to add a little contingency here, which is that you're going to select the random node from the sample to interview, and then you're going to, after you ask about their neighbors, you're going to try to immunize one of them. But if they're already immunized, you're just going to forget that ever happened and go back to step 2. There's a bunch of other choices you could make there, and we can test them, but they don't. But this allows us to do some interesting math if we assume this version, and also not doing that could like create redundancies and immunize people that are around the same area, which is not always good. Okay, so why would this be good and beneficial? We said we'd explore it more. So this is going to be a little bit of a technical slide, and we're going to get into some network science mathy stuff. So consider a case, which is fairly common in the types of networks that we would want to immunize, where the network is quite positively assortative, which, as we said, means that high degree nodes connect with high degree nodes, low degree nodes connect with low degree nodes. The network is also heterogeneous in degree. It means that if you take the distribution of all the number of contacts of everyone in the network, it has a high variance. And the network is also sparse, which is really common in pretty much every network that you're going to find in nature. It just means that the mean degree is much less than the total number of nodes. Basically, like most people don't have anywhere close to as many friends as there are people in the world. So the combination of the heterogeneous degree A and the sparsity, heterogeneous degree B, and the sparsity imply that the majority of nodes have a degree lower than the mean. This is because the minimum degree is 0. If the network has a variance that's quite high, then that's going to skew that distribution and implies that most nodes have a degree lower than the mean degree. So if you're acquaintance immunization, you're going about your day and you're going to choose randomly from all nodes. Acquaintance immunization would typically interview one of these low degree nodes that comprise the majority. That's what's going to happen on most days. With positive assortativity added to this scenario, this low degree node is also going to, more average than not, have also low degree friends. And so the immunized node is also more likely to be low degree, and that's bad for acquaintance immunization. So what we do is we use this modified snowball sampling procedure, which is snowball sampling plus this sampling with replacement added to it, in order to avoid this first misstep that acquaintance immunization makes, where it chooses these low degree nodes from all nodes. And instead, we're going to create a sample that is biased toward very high degree, and that leads us to generally select high degree nodes to be the interviewed nodes, which in positively assortative networks is going to lead to the immunized nodes also being high degree, synergizing the friendship paradox and the assortativity instead of having them battle it out. So we are going to simulate what that looks like, and we wanted to explore these parameters that we've noted and explained why they matter. We have this assortativity parameter. So this is these networks that are synthetic, which we use to create a full parameter space so we can explore everything in detail, go from very, very negatively assortative. These kind of things are almost never seen in nature, to very, very highly assortative. These is actually not the actual assortativity. It's a parameter that corresponds to assortativity. So the networks in this area are not 0.9 assortativity, but they're quite high. And what we see is that as we move from left to right in this parameter space, S4 becomes better than acquaintance. And how we're measuring that is the ratio of degree immunized at an arbitrary step 200. It's true for most steps until you get into a very high level of degree of nodes immunized. 200 is just arbitrary. S4 is better than acquaintance, as we see from the ratio of degree as you go from negatively assortative to positively assortative. At this middle here, they're even, and in the negative realm, acquaintance immunization is a little bit better, and the size of this effect gets stronger the higher your variance gets in the network. So this is a synthetic family of networks that we created bespoke for this project that allowed us to explore these parameter spaces. We also confirmed this for the most part with a series of benchmark networks that we collected from several other projects that are found in like nature, off the back of a truck, or whatever you want to call it. And these empirically observed networks mostly follow the same pattern, although with more noise and a couple notable outliers here, where this network is extremely negatively assortative, and yet S4 is doing quite better. And we're actually going to skip why that is, because it gets into serious math weird stuff, but it's in the paper if you'd like to read it. Tests, yeah. But generally, it confirms the the synthetic network result. So the evaluation metrics for S4, if you've noticed throughout this chapter, have been just the degree immunized. And that happens to correlate with how well that immunizing that node does for reducing outbreak size, but it's not directly correlated. It matters a lot, or it is directly correlated, but it matters a lot based on the specifics of the situation, based on the disease model, based on the network, a number of other things. We used it because it allows for generalization, so we don't have to do a huge parameter sweep of a billion different networks and disease models. And it also allows for analytic calculations, which didn't make it into this presentation, but it allows for some cool math. And that's all well and good for inventing the strategy, proposing it, and getting people interested in it, and for academic publication, which that's good for. It's not necessarily good for policy, where you actually do really care about the specifics. And what we see from the appendix of this paper and from the appendix of the first paper is that while a lot of the results are similar, throughout the size matters, and that can be a big difference in what policy that policymakers are going to want to choose based on your different types of network and disease models, et cetera. And so for policy implementation planning, we care very much about the specifics of the situation and the particular metric that you're evaluating. So what do we do when we care about the specifics? We can use agent-based models. So you can think of agent-based models as a bit like a video game with no player. Basically, you're coding a bunch of rules that follow stochastic patterns with a bunch of agents that just play out basically a video game, you can think of it, and you set it up a bunch of different to run a bunch of different simulations, and you are trying to mimic aspects of the system, and you can add a lot more detail into an agent-based model and have it still be tractable, which is not true about a lot of mathematical models that want to do the same thing. So that's what we're going to look at. Our last chapter is moving out from applying specific strategies on a general system to applying general strategies on a specific system. And that specific system that we're going to be looking at is COVID-19 during the Omicron wave. As we can see, people did care a lot about COVID-19 enough to write many different papers about this one specific situation. It's not always about these general approaches. Sometimes you just are committed to doing whatever you can to fix one thing because it's a big enough thing that millions of people are trying to do it. What we did in this paper is we're looking at COVID during the Omicron wave of December 2021 to February 22. We're examining counterfactuals to look at what we could have done at the time with the tools that were available. So now we're going to get into some specifics of the model. With agent-based modeling papers, a lot of the content is just like what you did for the model because it is quite detailed. So this is going to be most of this chapter's talk. We simulated a ton of different interventions, all of the ones that were really available at the time and being talked and discussed by policymakers. We have a number of different ways that vaccination was implemented, and changes in vaccination could be pulled as levers. You had the starting vaccination rates, which could represent how preemptive an approach was. You have the uptake rates of both the first dose and the booster. You have the starting date of the first dose and the booster for different age groups. So that could represent the FDA passing the emergency use authorization earlier, despite some protests by some scientists who are worried about safety. And also, we have the vaccination. All of these things are broken down by the demographic allocations that were happening at the time. If you remember, your age mattered when you could get these things. It's all programmed in. The scheduling matches up. The rates match up. We have throughout the model, all of the rates are going according to as they went from the CDC data, except we're multiplying them or dividing them or shifting them over according to these levers that we pretend to pull. Another thing that we're simulating is masking. So both the fraction of the population wearing the mask as well as the quality of the masks available Potentially the government could have encouraged masking or made more mandates, or they could have just passed out better masks. We also another thing that could have passed out better of is antigen tests, or spent more money creating them and distributing them. And so we have different numbers of those tests in the system, and also different specificity and sensitivity depending on what fraction of them are antigen and PCR. We also have various different ways of allocating these tests. So like, for example, one way that we allocated them was like randomly, or we allocated them by first you give tests to everyone that had an encounter with someone who was positively tested, give them more to older people, etc. Another thing that we can check is the quarantine guidelines, which were in discussion at the time. If you remember, they changed it to 5 days around that time if you had no symptoms or had recovering symptoms. And so we checked what if you didn't do that. And we also we're simulating shutdowns of various different locations that correspond to types of contact, settings of contact, school, work, and social. Another thing that we're interested in for agent-based models, as we talked about, is the evaluation metric. So with agent-based models, unlike a lot of other models, you can really look at any evaluation metric that you want. And so the ones that we were interested here were the epidemic size. Obviously, that's pretty much most models that you're talking about that are something like an SIR or have a recovered state, is the epidemic size, where that's just the total number of cases at any given time, or total number of cases total that have occurred. But also, we're also with COVID especially, we were quite concerned about the scale of the epidemic peak, the maximum number of cases at any one time, because that has implications for the hospital system and can cause a lot of unnecessary deaths that can be avoided if you just keep that number just below the maximum capacity. And so how we simulated this, there's a number of different big parts that each for their own big lifts. This is going to be a really simplified version of what this actually involved, but we have everyone connected to a number of different people based on a ton of different information. We leverage these synthetic populations to create highly accurate demography of agents, and we generate realistic networks of contacts between individuals across multiple contacts, home, school, work, and other social, whatever you want to call it, using nearly a dozen data sources for accurate distributions and mixing matrices that were collected from various different US agencies and other sources, like labor, like how many people are in work at a given age, what are the sizes of households, how are those households composed, etc. The individuals, besides these connections, the individuals in these populations are agents, so they have a lot of their own attributes. And so they have a suite of heterogeneous factors contributing to what we care about in the simulations, which are their susceptibility, their transmissibility, their reactivity in guideline adherence, and in care-seeking behavior. So as you can see, what that corresponds to is like what vaccine they had, whether they had a booster, how long since they've been vaccinated last, do they wear masks, their infection state, their base transmission rate, which can differ depending on the biology, is drawn from a distribution here. What type of illness they have that comes more in the disease, whether they go to work, and if they do so, are they working remotely, whether they go to school, and if they do so, is it closed? So now the relevant population, let's talk about how the disease was modeled. We used what is called an SEIRS model. It was modified, so SEIRS stands for susceptible, exposed, infectious, recovered, susceptible. So it means that nodes can be in any one of those states, except in our case, the infectious is actually broken up into 3, where nodes can be pre-symptomatic, regular infectious symptomatic, or asymptomatic, and that affects their infectivity as well as their latent duration. And those are calculated from parameters from literature and then calibrated to fit CDC case data. The first key finding of this study is that social distancing, closing a bunch of stuff, and also increasing mask wearing by a ton and the quality of the masking are both very effective. this is not surprising. These are the most drastic measures that you could implement. They were extremely effective, but the size of this effect is from doubling the number of places that were closed, and also quadrupling the number of mask wearers. So those are very effective, but they'd also probably be impossible or extremely political and economically costly to implement. So it is important instead to evaluate which combinations of policies can be put in place with few difficulties and compare them to these singular but more difficult policies. One soundbite heard at the time was that we were going to vaccinate our way out of the problem. But the vaccine hesitancy of many Americans made this difficult, and pushing it further with mandates and various different things had some divisive political costs. However, we see from this comparison, at least in this model, that if instead we might have focused on those who were willing to comply with those recommendations and provided them with better resources of access to higher quality masks for those who were already masking, and with boosters for those who had already proven they are willing to be vaccinated, that would have been comparable to if we had increased the general vaccination fraction of the population. More generally, another key finding is that the timing of the policies is also crucial for pandemic response. Here we investigate the impact of having a higher boosted population prior to the start of the Omicron wave, the boosting plus line in green, with an additional comparison line in yellow, which adds, in addition to this preventative measure of having a higher boosted population to start, the marginal effect of also increasing the rate of vaccine distribution and boosting after the beginning of the Omicron wave as a reactive measure. And what you can see basically is it does nothing. Like, it's the boosting in the beginning that mattered. Adding the increased rate of boosting and vaccination after you'd already started the wave did very little to add to that. And they're both compared to a baseline of what actually happened. So those are the key findings. There's a bunch of others. It's a huge model with a bajillion parameters. You can fiddle with it, and that's sort of the point. It is not really meant to be a forecasting model to try and ask what exactly would have happened if we had done this and this. It's more asking, well, if we want to play around with what are the scenarios and combinations of these things, you can get a general idea of what might have happened qualitatively. And so we call that a policy laboratory. And an important aspect of that is the exploration of this wide range of policy formulations, as well as allowing us to make claims that are robust to the uncertainty, that we're not claiming to be able to, if we're not claiming to be able to forecast, we want to at least be able to say with certainty that these policies are pretty consistent, even assuming the amount of uncertainty that we acknowledge. And so what we do for that is we have a ton of different scenarios simulated, and then we say which policies are generally ranked higher and what are the general orderings of these policy combinations. And we call that robustness of these policy rankings. Finally, one thing that I was particularly interested in this project I came into the project when it was already, there was an R version of it already built in procedural R. And I came into the project and I ported it completely into Python, into a modular object-oriented programming style from the procedural R, and implemented speed gains with various different C-ification of things. And what that allows is flexibility in the model. And it allows us to pivot from one question to another as things come up in the real news. And so that happened several times throughout the pandemic. We started in the summer of 2021, and several things happened between the summer of 2021 and when this was published. Some of the bigger ones was that we added to the model the ability to have all of the different factors be correlated with each other. And also we added to the model the waning immunity as people started getting sick again for the second time, which wasn't true in the summer of 2021. And also we added immunoscape and boosting and all the boosting scheduling as boosters became available. So that concludes the research chapters, and I'm going to just draw a couple of conclusions if I have time. Another 4 or 5 minutes, maybe. Okay, 3. So I'm just going to conclude sort of lessons learned and what I want you to have some take homes with this. There's a lot of future work that can go into this. As I mentioned, this is an attempt to bring the sort of abstract mathematical ideas from this field into a bit more practical terms, but it's a long way from that. As you can see, like the second paper was quite abstract, but it was a first attempt at a strategy which might eventually be implementable in practice. And so there's a lot of work to be done there. What we talked about during the trace chapter several times was like things are costly. And what do we mean by that? So like we can estimate, oh, this thing might have been politically costly, or this might have cost a lot of resources. We don't actually have empirical anything to say about how costly that would have been. We didn't have an economic model attached to that model. We could have. And I think that in the future, if you want to build something that is really caring about a lot of the specifics, I mean, that's a lot of what people are talking about now after COVID is a lot of the negative externalities that you could have simulated by attaching economic or other types of models to that project that could estimate economic costs or test score decline or mental health impacts, whatever you want. And the flexibility and object-oriented programming that helps. Another really important negative externality is inequities. Like COVID caused a number of health disparities between different populations. And that was something that a lot of people cared about. There was a task force about it, and it didn't really get solved. And so that would be something that I think we would want to be one of our next first steps if we wanted to implement something new. Another thing I've been really interested in recently is that a lot of this like politically costly, whatever we're talking about, really comes down to what we can think of as a collective action problem, which we've been doing a little work on recently. Basically, the idea is that it's sort of game theory. It's like tragedy of the commons kind of adjacent, where you where each player is a country or a state or whatever, and they have to trust that all the other players are going to do as good or better of a job than them, or they're sort of wasting their efforts. Like Florida benefited economically from having lower prohibitions. And there's a bunch of stuff that I'd like to do there. Another really direct aspect of future work that we could do is take our first 2 papers and change the way that missing data appears in them. They was approximated just for a first step as having nodes missing at random. That's not realistic. Nodes aren't missing at random. Oftentimes in these kinds of studies, you have nodes missing demographic because you have the researchers speaking more English than Spanish, and so people that are more Spanish speakers are less likely to want to talk to the researchers, something like that. Nodes could be missing by group because of some identity or like or geography. There's various different ways that the nodes can be missing, and we can test the methodologies of our first 2 papers under a number of different ways that data could appear. But probably more prudent now that I have learned from John Gabb's class, in that case, something you might want to do instead of actually just directly testing it, assuming that you have this missing data, and working from just that assumption is you could make an attempt using Bayesian methods to try to come up with you could use Bayesian inference of network structure, whereby we would similarly approach the immunization under missing data problem from the starting assumption that we would have imperfect data, but rather than develop a strategy specifically for that, we'd use the Bayesian methods to infer the posterior distribution over all possible networks compatible with the observations that we had, and then maybe sample from them, sample from that posterior, and then simulate outbreaks across the samples, weighting them by their probability in order to make generalizations about how effective these strategies would be based on information, not the information that we know is bad, but but our best guess of what the true information is based on the information we have plus the knowledge that it's bad. I'm going to get to a point, I might run out of time, but I would like to argue that there's a real need for this kind of research now. As you might have seen in Milo's talk, there's the encroaching dread. Oftentimes people think in their PhD that the situations of the science is going to get better as time goes on throughout your PhD. And in my case specifically, the opposite has happened. So when I started, Reddit and Twitter data were freely available. During COVID, at least, there was a ton of new mobility data that all these companies were sharing in order to help fight that effort. And now that data is gone because LLMs are price pointing them out, academics out. Privacy concerns are making people less likely to want to share their data, and then the companies are not sharing mobility because people have forgotten about COVID, so it's not like beneficial to them to do so anymore economically. There's also a number of crucial decades-old surveillance systems that are breaking apart in front of our eyes. Right now, we have highly pathogenic avian influenza that is everywhere, but nowhere do we know it is because the farmers are not testing because they have no incentive to test. They only get bad things if they get positive. Also, ProMed is shutting down, which was part of the warning sign for COVID early. We would have been maybe a week later knowing about it if we hadn't had that, and it's shutting down. So one of the reasons that might happen is that people are reactive. The infrequent nature of public health emergencies combined with the bimodal distribution of outbreak sizes in epidemics, which either fizzle or erupt, creates an unfortunate political paradox where public health policymakers do our job well, it looks like we spent far too much money doing it. And then those who put that funding in place get chastised. And when an outbreak does occur, rarely are the policymakers responsible for removing that funding still empowered to take the blame. However, things aren't always bad. There are a number of really cool initiatives that have come out of a lot of funding that came out when we were reacting to COVID. Things that have existed for a while but are gaining more traction, like think tanks like Brookings and Rand that are able to work between this divide in academia and policy. There's also a ton of new centers, 13 new large centers, academic and across academic through the CDC. There's also 17 coming through the NSF. Another thing that I'm really excited about is the Center for Forecasting and Outbreak Analytics, which is a new branch of the CDC, which was founded by the Biden administration after people sort of were like, wait, the CDC doesn't predict outbreaks, like then who does? And they were like, okay, we'll do it. And so they're starting and they're recruiting heavily. And I'm lucky for me, I was part of that recruitment and I will be working for them shortly. And so I can start taking some of these principles that I've outlined and learned in my PhD to the real world. And I'm really excited for that. And I never would have gotten to that point if it weren't for all of these acknowledgements. Thanks to all of my formal mentors, Laurent Ebial, which I work very practices. My undergrad mentor, Andrew Black, ACB, Kirk Dombrowski, another undergrad mentor, all my formal mentors. I also had a number of people that were my peers or a little older than me that I really consider strong mentors. There are also a number of people that I like to think that I helped guide in their own path through academia or data science. Thanks to those people who let me try my hand at passing on some of my own wisdom, it was probably more important to my fulfillment than you can know. And while in my civil service career, I hope I will have more opportunities to do this, it is probably my greatest regret of leaving academia proper that I won't have the chance to be a more formal mentor to my own students. Thanks to all my collaborators, especially David O'Gara, Kevin Andrew, and all of the Reddit bandits. I spent more time on Zoom with these people than several people I've dated. Being part of the Reddit bandits was the warmest and most joyful collaboration experience I've ever had in my life. Thank you to all the mysterious old wizards who let me borrow their powers for 30 minutes to ask them about their own specialties. Jane always was willing to give me a tip for data visualization. Guillaume helped me turn my puny millions of simulations into billions. Ben, Josh, Michael, and John helped me become a VAC monarch. And especially thanks to Bren Case, who always was there to help with LaTeX, with UVM bureaucracy, and with life. Thank you to my family, who was always there to make sure that I was at least okay. Thank you to the friends I haven't mentioned in these, who, especially the ones that helped me through the last couple of weeks, encouraging me, giving me a read through of a couple pages. And a special thanks to people that like really rescued me from various different portions of days where I was delirious from energy drinks and really needed to be brought a snack or something. Liz, Sasha, and Sam Brewer. Yeah, thanks.
Now is an opportunity for open questions.
Oh, yes.
On the on the results of your agent-based model, it looked like there was one, it looks like there's one that's labeled all. Is that like all interventions? And if so, why is it not?
Okay, yeah. So I should have. I don't think I explicitly said this, but so an important aspect of the distribution of these policies is so we simulated tens of thousands of policies, and we had to just pick some to be like corresponding to things that were talked about at the time. And so what because they don't always correspond to like the same thing, but they can sort of be grouped as like a small increase to a policy or a like really drastic increase to one particular policy. We called the differences in that that policy plus or that policy plus plus. So in particular, what vaccination plus means is just taking the fraction of people in America that were ages 17 to 50, I think, or something, and making their vaccination rate equal to 50 and above. So that's vaccination plus. Vaccination plus plus is much more dramatic, where we do that, and then we also take the people ages 5 to 17, and we make their vaccination fraction equal to what the 17 to 50-year-olds was, and we also vaccinate the 0 to 5-year-olds at the rate of what the 5 to 17-year-olds were, which corresponds to at that time what that would have meant, because they were not able to be vaccinated at the time, would have meant much more rushing the emergency youth authorization for that age kids, and that would have been costly. Even if it worked, it would have been a politically risky move, and if it ended up that those safety authorizations which eventually passed led to some serious complications with some kids, and some kids would have died possibly. Didn't happen. Vaccines most of the time don't do that. But if potentially they're not tested first, it is possible, especially with new technologies. And so we did test them, and they worked. But if we didn't know that at the time, and we could have rushed that, maybe potentially saved lives, but also it could have cost people's confidence in vaccines, especially for their children. And so anyway, I'm getting sidetracked. So all plus is just means take all the strategies and improve them a little bit. So take the little addition to each strategy and add them all together.
As opposed to like a strong increase on like one particular.
Yeah. So all of the plus pluses are pretty big bumps. Some of those are more, even though they're big, they're more feasible. Like the mask efficacy plus plus just means everyone who was wearing a cloth mask now wears an N95. And so like that you could imagine happening. Like it's just access basically. Yeah.
So we've been talking a lot about infectious disease and public health today, and you've referenced a few other domains where this is particularly relevant. But I'm curious for you, as you've really dived into these methods and thought about a lot of different domains where doing these interventions on networks is really helpful and important. I'm curious for you, what do you think is the most applicable next domain that these methods that you specifically worked on would be translatable to, or where do you think another domain could really be fit?
That's a great question. So I mean, so a lot of the target immunization research, pretty much almost all of it, assumes that the immunization is perfect, which means that the immunizing a node means that they cannot be infected, which is not true about vaccines. Vaccines are pretty effective, depending on the vaccine and the disease. But that's another constraint that is sort of overlooked by this. But we've developed a lot of research assuming that, and so it would be great if we can apply that to a domain where that is true, and that is true in a number of domains. So one example is on social media where you're banning a user. That is an effective vaccination strategy. They're gone unless they create a new account, but you can protect against that. And also they lose all their followers and whatever, at least for a while. There's a bunch of others, but that was the first one that came to my head.
There's a question online from Philip. How applicable do you think is the S4 model to knowledge-related epidemics, like memes, spread of scientific knowledge, and disrupting insurgent cells?
Well, I mean, at least for the way that we evaluated S4 specifically is for most of the paper, except in the appendix, we evaluated it just as the degree of the node immunized. And so that has nothing to actually do with the specific type of outbreak model that you have. And so while the examples listed by the question asker have completely different models of spread compared to a disease model, which has an independence assumption for each different interaction. There's nothing that says in at least part of the S4 that we showed that model mattered. And so it's just high degree nodes. And so if immunizing high degree nodes to stop these types of spread is effective, just like it is effective for stopping the spread of disease, then S4 would be a good strategy. April.
I thought it was interesting that you mentioned like testing a lot of different parameter changes and combinations for interventions on the agent-based model, but I don't remember you mentioning changing the immunization strategy.
I have a whole slide.
So I'm curious if that was just a limitation of the model, or
Oh wait, for the agent-based model specifically?
Yeah,
Oh, okay, no, yeah, so we did, well, so you can think, I mean, so first of all, that's sort of a little bit of the point of the first paper, is that we don't typically do like immunization strategies in real world. And part of that is a factor of how many immunization units you have. And so at least during the Omicron, there were still not as many vaccines as we would have wanted, especially in the global South. But in the United States, there were enough vaccines that moving them around to different categories wouldn't have been as effective as if you had much less per unit. However, we did sort of have vaccination strategies you can think of as, if you remember, healthcare workers were vaccinated first, older people were vaccinated first, school teachers vaccinated first. So as I mentioned, healthcare workers and school teachers happened to be high centrality nodes for reasons that are sort of intuitive to policymakers. And so you can sort of get away with having that be like an immunization strategy by recommending that because it corresponds to one. Vaccinating older folks, however, is actually maybe not very effective as an immunization strategy according to the metrics that we evaluated on. And that actually brings up whether those metrics are the ones we care about. So vaccinating older people, while maybe they have less contact than some other people in the population, vaccinating them with the aspect of vaccination that prevents serious illness and death, that was very important, at least in the short term, for their health. And so you could do a calculation and do a simulation and see if the total number of cases increase by choosing older folks at the time instead of some higher contact individuals eventually led to more deaths than were saved when that occurred. But at least at the time, it saved a lot of lives and was politically beneficial. I mean, you can't imagine the president who has a lot of voters that are in the older area saying to them, no, actually, we're going to give them to these 30-somethings because they are partying harder than you. You're going to give them to people because they are going to die if you don't. But we actually did implement amongst the parameter combinations we looked at. We did change some of the vaccination strategies you can think of. We broke it up by demographics a bit. We didn't actually have. You could include in this simulation like the nodes having jobs. You could assign them all jobs. The data wasn't there for us to be able to do that in a way that was meaningful, and so it would have basically just been randomly assigning them, and the results of that wouldn't be as meaningful. But the vaccination strategies that we did implement are by age demographic. We moved those values around a bit. Also, sort of similarly in terms of like strategies, the way that we implemented who got tests and who got traced did really come down to the same kinds of strategies. And so we did implement several different methods of allocating those tests, which were in high demand at the time. $50 at CVS, now they're free. And that comes down to more closer than you would think to this kind of work that appeared in the first and second chapter. Oh, okay. Bryn already asked one, so
just out of curiosity for the agent-based model, how many agents were you simulating per?
Good question. Yeah.
Along with how long on average did these take to run?
No, yeah, great. I had a slide on that, but I couldn't find. Initially, I actually asked Melissa. At one point I did like a full code runtime complexity and memory analysis, and that was lost when my computer broke. But I can tell you, and there's in my notes somewhere, it says that we increased the runtime, we decreased the runtime of the model when we CIFIed it in Python compared to the procedural R by 2 orders of magnitude. So like in the 100 speed improvement, and on average, these simulations would take anywhere from like 2 seconds for the 3 months-ish to like 20 seconds, and it depends on the outbreaks. And the number of agents that were simulated was 50,000, and so note that there's less than 50,000 people in the United States. So what modelers you call this is like a representative model where one person is maybe supposed to represent more than one person. That's maybe an excuse. I mean, you just can't model that many people and do that many parameters. It's a trade-off. Like the number of connections increases as n squared as the number of nodes, and then that increases the runtime complexity in a squared fashion. And so 50,000 is much many as we can do. There is some really interesting research about how to do that a different way, where you are you are simulating as many nodes as you need to, basically. And so when the outbreak gets bigger, you simulate less nodes because it slows it down when it gets bigger, and B, you need less to capture the kind of behavior that you're aiming for. Laurent is working on this as well in a related thing, not an agent-based version of it. But you can adapt the number of nodes based on a number of factors that allow you to say that this is realistic for the current thing that's happening. And so when nothing is happening, when there's very few outbreaks, you actually are simulating the 333 million people that live in the United States. And when there are a lot of outbreaks, you're simulating 5,000 or whatever. And it stays the same speed throughout.
In the interest of time, I'll suggest that we wrap up the public Q&A. You'll still have access to Sam in a little bit after the private portion. So please join me in thanking Sam again.